Recording in progress.
Okay, so homework was hopefully not too bad. Average rate of change for number 1, that's pretty easy. Just find the slope between 0 and 2. And for B, between 10 and 12, easy peasy. Let me see if these are up in Schoology right now. I think they are there. It should be. Yeah, they're up in Schoology, so that's good. Going back to the solutions again. Wait, shoot. Darn it. Why'd I close it? Hold on. Okay, for 2, this is also average rate of change for PQ1, PQ2, PQ3, PQ4. Looks like it eventually gets close to 50. So each slope represents average speed. And so approximately you could say the question's actually asking for, let me go back here, sorry. What was the question asking for again? It was asking for the estimated speed of the car. So we're all good there. For 3, now you're actually finding the instantaneous rate change, or what we call the derivative, or the slope of the tangent slope of the curve. And this is the a different form. This is called the alternative definition of the derivative. It still does the same thing, or you could do what we did in class for number 4 and 5, I suppose. But here they're forcing you to use this method. Not that hard. You got it. Work it out. Factor it. All's good. For number 4, that's easy peasy. Just do the derivative. So using the slope of the tangent line, work it out. Likewise at 5. For 6, you got that one right there. So again, just work out the slope of the curve or tangent line, whatever you want to call it. But you got to do it in plug in 6 afterwards. You get 1/4. That's the slope of the curve there. Sorry, if that was 5. I meant to say 6. Yes, you want it in a more general sense in terms of A. So you do that. You get -1 for A minus 1 squared. Then plug in, so I said equal to 9 to solve for A. What values of X? We got a slope of -1/9. I guess that's 4 and 2, looks like. Yep, 4 -2, my bad. And then you're asked to find showing 6 more and graph the tangent lines. Okay, that's fine. Not hard. And then part D, I think it's asking for horizontal tangents. No, what happens if A is approaching positive or negative infinity? If A is approaching positive or negative infinity, overall this gets to 0. Okay, which makes sense because those are the end behavior asymptotes. And then lastly, number 7, graphically and in words, explain the difference between the average rate of change and instantaneous rate of change. So average rate of change is the slope of the secant line. The instantaneous rate of change is the slope of the tangent line. There's a difference between the two. And it's also how fast somebody's moving at a particular time for instantaneous rate of change. For average rate of change, is on average. What do you see as a rate of change on average in 2 distinct points? So, and that should say number 7, not number 6. I don't know why it says that. So that's a typo, or a hand wrote this. I think Ms. Jones did that. Anyway, questions? No? All right, now I can close down. All right, let's get to the notes. So we get out at what time? 2:30 or 2:35? 35, all right. Okay, so I think we can get through this for sure. You'd be good. Okay. Sure, of course. So the notes. So guys, these notes will get us through the whole year. The homework's only for this current unit. I am going to break this into 2 small tests. So this test, I'm not sure when it'll be. I'm going to try to aim to do it. I think April 29th is kind of cruel because I think it's right after prom. So I might do May 1st instead, if that's okay. I think that might make more sense. So anyway. Okay, the derivative. I've already started talking about, but we're actually going to get more formal about it today. And really, it's just that limit definition I showed you guys. This is called the limit definition. This right here is called the limit definition of the derivative. You'll hear that phrase used a lot in calculus. On the AP exam, many times they will actually test you on that knowledge. Like they'll give you some weird limit problem. And I'll see if I can dig something out that it might be. Not take long, I'm not too familiar with the AP review stuff. It's been a while since I've used it. But sometimes on a multiple choice question, you'll see a limit, and you think to do a limit like we did in our last test. But what you have to recognize is that, wait one sec, this is actually a derivative. And then you learn all these derivative techniques later in the spring. I'm going to teach you techniques that will make you find it much more efficient than this full limit nonsense. I know it's nonsense, but it is kind of nonsense in some ways. I'll teach you other techniques that will make the problem more efficient, but your job is to be able to recognize, oh yeah, this is a limit definition of derivative. This limit, it's not really a limit. Yes, it is, but it's really more a derivative. So call it a derivative, or more specifically, the instantaneous rate of change. So for example, if you're driving from here to Los Angeles, say it's 400 miles, and let's say you're going fast. So you're going you get there in 5 hours. From here to LA, 5 hours. So 80 miles per hour, right? That's your average rate of change. But you didn't drive 80 miles per hour the whole time. I highly doubt it. You probably stopped to go in and out, stop to use the bathroom, stop to go check out this. There's no sites on the way to LA, but anyway, maybe stop somewhere. Or maybe you had to make a phone call. I don't know. But there might be a moment where you drove 100 miles an hour. And you saw the cops, you slow down. Or maybe, or that's me. Or maybe you get traffic, like right before you get to LA, you get some traffic, right? So you gotta slow down. So that's what instantaneous rate of change is, that moment of how fast you're moving. So right now, the average rate of change will simply be the slope between P and Q, or in this case, it will be f of A plus H minus f of A all over H, because you're subtracting A plus H with A. Whereas here, this will be a limit as H approaches 0 of f of A plus H minus f of A all over H. So it's almost the same thing. Sorry, my handwriting stinks here. My apologies. It's almost the same thing. The only difference is you're doing a limit to the average rate of change. So this is average rate of change, right? Because you're trying to find the slope between these 2 points. But what you want is you want H to approach 0. You want Q to get closer to P. As Q gets closer to P, the line becomes less of a secant line, becomes more of a tangent line, right? And that's what we're trying to get out with the derivative. We want the secant line to transition to a tangent line. That's what we want. Notation. Notation is very important, because I want to make sure we're clear on this. And I'll remind you guys, because it's probably new to you guys. So let me take care of the stuff on the bottom. So you know how I'm saying this. I know, right? Phonetically, I know. I got a 7-year-old that's learning to read, so I got to do things phonetically. So anyway, f prime of x, y prime, dy dx, df dx, d dx of f of x. You can say that too if you want. I don't, because I'm lazy, but you can. What? Yeah, it's okay. Yeah, either way is fine. They're all the same thing. We call this the derivative. Okay, we call this the derivative. The derivative is simply an instantaneous rate of change. Instantaneous rate of change. We do use the word differentiable often. Differential means you're able to differentiate. Right? You're able to do it. So differentiate is another way of just saying you can be a derivative. But the derivative is a noun. Like, if you want to, it's like English class. Derivative is a noun.
differentiates a verb. Differentiable is an adjective, right? Or differentiability, well, actually, it's back to now. Not even adverb, but differentially. Yeah, there we go. Yes. But yeah, this is this, right? So this is the same thing, but instead of putting an A here, we're putting next. So this will get you actually the derivative as a function.
So that's the other thing I want to kind of emphasize too, because this is the one part when I took calculus many years ago, was first time I was a senior in high school, and then college, and I was kind of a space cadet as a senior. So just to be honest with you guys, yeah, I mean I just didn't really pay attention. Yeah. So let me explain what these, because the notation can be a little confusing. F prime of x. I mean, granted, I did go to a large public high school and a large university, so, but anyway, so I just got distracted. So this is going to be the derivative as an equation that contains a variable x, right? Whereas this here will be the numerical value of the derivative when x equals a being some number. Hope that makes some sense. When I use these letters, because that can be a little confusing sometimes. I want to make sure we have clarity on that. So when we're
Looking for f prime x, I want you to give me an equation. Like, okay, what is, okay, let's say y equals x squared is my equation. What's the derivative of y equals x squared? So give me f of x is x squared. What's f prime of x?
you gotta give me an equation, which by the way is 2x. But if I say, okay, well, f of x is x squared, and find me f prime of a, where a is 1, that means I want you to plug a 1 into the derivative afterwards. So I just want to make sure we're clear on that. So like this right here is actually going to be an equation. Like this is actually, or not, but like an expression in terms of x. I expect that for this one. And again, we call the output the derivative of the function f with respect to the variable x. The whole respect part, this is the part that's not going to be very clear, and probably not going to be clear until next fall. Unfortunately, I won't be able to. Unless you're interested, and if we get further ahead, we could talk about that.
It's a little tricky, but there are times where this letter will change a lot. And that changes the whole outlook of the problem. We're not there yet, can't really talk about it, but we'll get to a point where we have to separate these two different expressions, like we separate the numerals not there. That's actually not until like the spring of AD or BC, probably, yeah, you do the spring out there. But it's kind of like saying this in some ways. Delta y or delta x. It's kind of like that, right? And what does that mean? What does change y or change x? What is that? Right? So exactly, yeah. The change y or change x. And that's what derivative is, but it's more specific. It's at a particular point. So it went to 2 points and the first one to 1 point. Now we have a limit, so it can help us. But it's kind of the same thing. So anyway.
All right, so let's keep moving. All right, so what you want to do here is find the derivative, find the derivative and use that to find the tangent of the curve at x equals 5. So what we're going to do is this: the limit as h approaches 0 of f of x plus h okay. Now, if in case you guys forget, the expansion of this is this: a cubed plus 3. You remember Pascal's triangle? Have you guys ever done that? No, maybe not. I don't know. Yeah, so if you expand this, because we're going to have to do x plus h cubed, kind of a pain, minus x cubed, all over h. And don't get lazy. You got to write that limit notation until you finally plug in h to 0. So expand this x cubed plus 3x squared h plus 3x h squared plus h cubed all over h. Oh, forget about the minus x cubed. Okay, can I cross anything off? Yeah, and they should. Because now the top has a bunch of h's, right, that we can factor out. So you can factor on h, the limit as h approaches 0. By the way, we're not going to always do derivatives this way. We will have a more efficient way, trust me, we will. And we will talk about the semester. Probably in early May is my guess when we'll do it. Factor out h. What happens to the h's? And now I could plug in 0 for h. That is a terrible color. So you just get 3x squared. Yeah.
What's the difference between dy over dx and d over dx?
Great question, actually. I didn't clear that up. Thank you. But are we okay with this problem? Yeah, okay. Yeah, sorry. Yes, Oscar, that's a fantastic question. I actually was meaning to say that. So here's the deal. Dy over dx is basically the derivative, right? Not as a function, sorry, with respect to x. So it's going to be basically an expression. It's like your final results. That's exactly what we did, right? What was our final result? 3x squared, right? So that's exactly what we did. Now, d dx on its own, that's an operator. So basically it's instructing you to do the derivative. So when you see, like, for example, like, isn't square root an operator, right? It's a function too, like you write root x or root x plus 1, whatever. But the root by itself is an operator. That's what d dx is. It's an actual operator that you're going to apply to f of x. So when you see d dx, it means it's an operator. And in fact, actually, I might as well show this now to you guys. Let's see here. The graphic calculator does this for you too. It doesn't do it algebraically, but it does it numerically for you. If you do have a more advanced calculator, like the TI Inspire or 91 or what, or 92, like one of those really fancier ones, it actually will give you the symbolic. Like if you say, if I'm going to derive x, people say it's 3x squared. The TI-84 calculator actually just does the numerical value. So if I hit alpha window, you see option 3. And you see how it says B. It's really hard to read. This is a B over B and it's a blank. That's an operator. And then that's what you're going to put into the derivative. And then you're going to tell it, do it x equals whatever value. So like, for example, if I do x, and then x cubed, and I know that answer is 3x squared. We just did it, right? Now, what if I put 2 in? What do you think my output should say? 12, exactly, because I worked it out. There you go. But it doesn't do it 12 exactly. It does 12.001. What do you think the calculator is doing? Kathy, you have an idea? Kind of. What it's doing is it's actually it's actually not doing the limits. It's actually doing a secant line. It's actually finding the slope between 2 points, but 2 points are incredibly close together. So I think that if I'm not mistaken, I think the algorithm is this. let me clear this. I think what it's doing f of 2.00001 minus f of excuse me. Yeah, I think it's doing something like that. If I'm not mistaken, I think. I have to check my notes on this stuff, but I think that's what it's doing. So it's giving an approximation, which is pretty darn close to the real thing. That's the algorithm it uses when it calculates the derivative in the calculator. So, okay, now you've seen that. Let's try another one. Okay, let me tee this up for you guys and have you guys do the rest. So we're going to start by doing this limit as h approaches 0. Yeah, Ron, go ahead.
In terms of like all those different ways that we saw writing the derivative, this is all just asking the same thing. Right?
Yeah. And it's your own personal preference what you like to write. I'm lazy. I do y prime. That's kind of my MO.
And it's all the same.
But sometimes I do write dy over dx for certain problems where it makes sense from a notation standpoint, which again, we're not really having that conversation yet. But it's all the same thing. And yes, whatever you're comfortable with. Yeah. Yeah, it's totally up to you. I personally write y prime. That's what I do. So we're going to do this 1 over x plus h minus 1 over x over h. Okay, I'm gonna have you guys work it out. I'll freeze my screen and I'll share in a couple minutes. Find the LCD, by the way. We got that? Yeah, good. Excellent. Yeah, not that hard. Negative 1 over x squared. Love it. Easy peasy. Okay. Let's keep moving. I think the next one's a radical. Yep. Okay. Now, I think you guys are starting to get this pattern. Remember I talked about this yesterday. I kind of got ahead of ourselves a little bit, but like remember I said like y equals x to the n. The derivative would be this. This works specifically for polynomial terms where it adds to the base and ends in exponent. And it can be any real number, by the way. Your exponent can be any real number, but if your variable, your input variable is the base of the power, this is called the power rule of derivatives. Like 3x squared, if I move the 3 to the front, drop the exponent by 1, didn't I just get that? How about 1 over x? What's x as a exponent here? 1 over x? Okay, let's do it. Negative 1 times x and negative 2. Isn't that negative 1 over x squared? Yeah, right? It works. You can roll the exponent to the front and then drop the whole exponent by 1 to get the derivative, assuming it's of the form x to the n. It'll always work that way. We're going to talk about this when we get to section 3.3, which won't be until after our small test, not until for a couple of weeks. But I know you guys can look this up. People will tell you, oh, what are you doing? It's much easier this way. Fine. We still got to do the limit definition to respect it, understand how it works. But at least I know what to expect for the next example. Like root x, what's root x as an exponent? 1/2. So I expect this, right? X to the 1/2. Y equals that, then y prime 1/2 times x and negative half. Or 1 over 2 root x. I expect that to happen. I'm still going to go through the motions and do it. So I'm going to do root. Okay. So you guys do that, right? Let me freeze the screen. Let you guys do it. Conjugate stuff, right? You guys did it on the last test, so I trust you guys can do it again just fine here. What do you guys split up, UV?
Like if you had like two things added to each other, could you like split them up? That's the,
I don't understand.
like if you had x cubed plus x squared, would you get it on x cubed ends of x squared and then just add them? Yeah, you just. So it would be.
Wait, can you show me? Because I'm like totally lost.
Here, let me undo.
Is UV making up stuff?
Oh, do the derivative. Oh, of course, yeah. No, we're not there yet. Yes. Yeah. No, of course, yeah.
If there's a plus or a minus, yes. You can apply the derivative to individually each of those terms. You can't do times or division. There's a separate rule called quote product and quotient rule. We'll do that in May. We will get to that. Actually, that's when we do section 3.3. We'll talk about all the different techniques you use for derivatives. Okay, does that make sense, guys? I got it. All right, let's keep moving. So if you have a linear function, by the way, the derivative is just m, and that's just 2x. We saw in the last, I think we saw that in the last section of notes, if not mistaken. Because if you think about it, that's just a line, right? What's the slope of a line? M. And what's the derivative? The slope. So isn't the derivative of a line just the slope itself, right? It would be. And then y equals x squared, that derivative will be 2x. Generally, it would be 2x. And if you think about it from a graphical perspective, so let's say y equals x squared, right? Let's say it's at -1. That's at -2. That's at 1. That's at 2. If I drew a tangent line at -2, let's say, that's clearly a negative slope, right? If you plug into the derivative, what do you get for your slope? -4, right? Kind of makes sense. What if I drew a tangent line y equals 2? That looks like a positive slope, like a pretty steep positive slope, right? If I plug in 2 into the derivative, what do I get? 4. So you can see how, in the general sense, when you have the equation of derivative, you can then find the slope of any tangent line you want on that curve for any x value of your choosing, right? Because now you have a general function for the derivative that you can apply, or you can utilize to find a derivative. So makes sense from a graphical standpoint. Yeah, of course, it's a steep slope at 2, so or steep positive, but steep negative at -2. Okay, this is a big one. That's a big one too. This is important stuff. All right, let's understand the relationship between the graph of f and the graph of f prime. Okay, so remember, f prime is just a slope, right? F prime is just the slope of f. That's all it ever is. So let's say the graph off to the left is f, right? So this is the original function, right? And that's the derivative, right? Okay, we're going to graph the derivative from the original. Now, fortunately, the original is a piecewise function with a bunch of linear segments, right? You got 1, 2, 3, 4, 5. I got 5 linear segments. And each linear segment, we have an interval defined for, or subinterval. So -3, -4 is the first one. -4, -2 is the second one. -2 is the third one. 2 to 4 is the fourth one. 4 to 5 is the fifth one. And also, just to avoid confusion, we're going to use open intervals instead of closed intervals. Closed intervals didn't ambiguous because, like, if I close it at -4, yeah, you don't know exactly right. Also, another thing we'll talk about too, which I'm not prepared yet. Actually, I think we'll do that on Monday. You're not differentiable, but you can't find derivatives at corners. We're not there yet. We'll talk about that, but that's something you can't do. So we'll keep it open. And even the AP, because they know the ambiguity with closed intervals, they even say if they want open intervals, we can use that block, but they give you open intervals to avoid the ambiguity. Anyway, so let's just slope that for a second, guys. What's that slope that for a second? So we're just finding slopes. That's all we're doing. What was that? Okay, what about the second one? What about the third one? What about the fourth one? What about the last one? Well, you said -3 or -4? Yeah, I say 3, yeah. Okay, cool. So here's how you draw it. Are we okay with that? Does that make sense? I found the slopes, right? Just rise or run, right? That's like, seriously, like, you guys have been doing calculus since middle school. You have, just haven't realized it. Slope is a big part of calculus. So you want to draw this first, starting at -4 and going to the left. And then from -4 to -2, it's going to be 1. And then from -2 to 2 is going to be 0. Two to 4 is -4. And then
And you got the holes because it's not included, right? So that's your drift graph. Your drift graph will look like that.
okay. Makes sense? We're good? Yeah, cool. All right, let's keep moving. All right, this is actually one of my favorite problems. And it's actually a really cool simulation that I could pull up after I finish this problem, or actually after I finish example 6. I really want to show you this one simulation online that's really kind of neat with helping you graph derivatives and help you understand how derivatives behave graphically. All right. So usually when we do this, in interest of time, guys, quiet. In interest of time, we're not going to do it this way, but usually we have a bunch of rulers and we actually have you guys like actually calculate, like actually measure the slope. But we're just going to kind of do our best guess. Actually, I'll get a little smart about this. Let me do a straight line. Okay, what do you think that slope is right now? How far do you think it goes up and over? One, two, maybe 3. I don't know. What do you guys think? So, well, first of all, what's the x value today? No, I say it's -4, right? Yeah, actually, let's get the x values out of the way first. And we'll say the slope is we'll say the slope's 3. G's right here. Got cut off. All right. Okay. I'd probably say the slope is 2 for that one. How about C? What do you think the slope is there, guys? Sorry, -2 at C. I'd probably say it's 0. Right? I'd probably say 0. And probably 0 at E as well. Because flat. Okay, how about D? Yeah, probably -1. That's probably 1. And at 4, probably looks steeper. Yeah, probably 2. Okay. So now what I'm going to do, I'm going to plot those points, -4, 3. So this is F prime. So F prime are the y coordinates. Okay, very important. F prime values are the y coordinates. Okay, I kind of missed. Okay, I didn't do a good job graphing this, but what do you think the shape is roughly? Probably a parabola. Because the first graph probably is cubic. Again, this is an estimate, right? So I probably may have overestimated B, maybe, or underestimated C, A. So what can you say about the y values of the graph of F prime when the y values are increasing? When the y values are increasing, F prime is positive. When the y values are decreasing, F prime is negative. Think of like a roller coaster, right?
If you board the roller coaster, A, as you ride the roller coaster, are you going up or down? Up. So the graph is increasing. When the graph is increasing, F prime is positive. That is an important distinction we have to make clear. F prime tells us whether you're going up or down. So you're going up, so F prime is positive because the slopes have a positive slope, right? Sorry, the tangent lines have a positive slope. Then when you hit the peak, or you're 0, right? You have a flat line. Now you're going down. We're decreasing. We're decreasing what the slopes of the curve, the slopes of the tangent. They're negative, right? So F prime is negative, you're decreasing. Then you hit E, it flattens out, then it starts going up again. So when F prime is positive, you're increasing. When F prime is negative, you're decreasing. Okay, that's what you can say about the y values. Or you could also say the y values are positive here and negative here on the graph of F prime. On the graph of F prime, the y coordinates are positive when F is increasing. The y values are negative when F is decreasing. And then we have a horizontal tangent. There'll be an x-intercept on the F prime graph. So F prime equals 0. That'll be the x-intercept on the F prime graph. So you're asked to estimate the slopes at these different values. So, you're asked to match. So which of these 6 letters would have a slope of -3, would you say? Probably F. Which one would have a slope of -1, would you say? Which one would have a slope of 0? Which one has a slope of half, probably? How about 1? I'd try to say B and D. Okay.
So what I want to show you guys right now, just because to kind of break the monotony of these notes. GeoGebra. Yeah, this is a good one. I like this. So this is a kind of a neat little exercise. I'll put this link in school just so you guys can try it. So just reset it. Okay. So here's the deal. The black curve is original. Okay. This is the original function. And the one that's dotted is the derivative. So let's take a look at -6.
At -6, is you slope positive or negative here? Probably it's like negative, more, definitely less than -1. Probably -2, maybe, I don't know.
So I'm going to push that down to about -2. Okay, at -5, slope positive or negative, -5. But probably not as negative as before. Yeah, so I'll probably do that. Okay, and then definitely where's the slope? And I'm cheating. It's probably 0 here, 0 here, and 0 here. So I want the derivative to cross the x-axis at -4.5 roughly. And then is the slope positive or negative, -4? Probably about positive half, I'd say. What would we say the slope would be at -3? Probably about 1. And probably it's a little steeper at -2. And then it gets less steep at -1. And then even less steep, still positive at 0. And then it hits 0. And still kind of 0 at 1. Okay, at 2, it's probably negative. Probably negative half. At 3 is probably not quite -1. At 4, probably a little steep. It's probably 0 or close to 0. And probably positive here. Let's check my accuracy and show the results. I'm pretty darn close. Does anyone think they could beat me? Anyone try to beat me? Okay, who can beat me? All right, here. Here, let's give you a. All right, Captain, come up. Let's try it.
Yeah.
I think you probably will be. Wait. Oh. Good point. Ish.
No. Yeah, lower.
Wait.
That goes down really fast. Yeah.
It's like here.
I think you want the negative 5 value to be lower than 0 as a method. Yeah, no, when I go to right, yeah, that's it.
Yeah. That's like one.
Okay, wait.
That's and -3 seems like.
No, it's not.
Yeah, this helps you get more in touch with slope tangent lines and derivatives. So
It's like really
connecting the numerical value and
-3. Okay, that's at 1, I think. No, it looks like. Yeah, this looks like.
Higher.
I think
Yeah, it shouldn't be like it should be.
Okay, wait, I think.
That should be a half.
I think -1 should be down. Yeah.
So -1 is 0.
Yeah, one is exactly.
Yeah, I'll say so.
Yeah.
Oh, yeah, negative one should be lower than.
That should be lower than.
No, no,
I
yeah,
think it's better. It should be more smooth.
yeah, it should be.
It looks like -1.
Yeah, negative one. Yeah. Three is like negative.
A little bit more.
They're all pretty much very similar. Yeah, there we go.
Yeah. Four.
That's a lot more.
Yeah, so it looks deeper there.
That's almost -2. Yeah, I feel like 2 should be.
That kind of looks weird, but
I think 3 can be.
Five looks like negative one.
Wait, why does it go up? I think you can move 3 down. I think you can move 2 up. Because 2 is like.
You guys think it's confusing?
I think 3 can go down a bit. 3 should go down. Like, yeah, 1.5. No,
That's a little better.
Why?
Five.
3 down, like, yeah, but 3.
Yeah,
All right.
yeah.
check accuracy.
Oh, maybe.
You did?
So,
Pretty good. Good. Well, pretty good. Very good. So, all right, cool. All right. Let's wrap up the notes quickly because I just want to kind of get this done. Just to get a sense of completion here. All right. Now, we also talked about derivatives from a one-sided perspective. So there's a right-hand derivative and a left-hand derivative, just like I had a right-hand limit and left-hand limit. And we'll talk more about that in 3.2. But this is abbreviated as RHD. That's abbreviated as LHD. And look at the superscript. So what this means is that H is positive for the right-hand derivative, H is negative for the left-hand derivative. So if I were to find, actually, we'll do that for example 8. So we're not, let's hold off on that. Let's actually do example 7 first. Example 7 is a different type of problem. Example 7 is, what's the slope here? Yeah, so you go from -4. Hold on. What was that, sorry? No. That's for up above. And that's -1. Kind of hard to draw that. Here we go. Okay. So, right. So to talk about when a function is differentiable on a closed interval, that means that the functions can the derivative can be found at every point in that interval. If you see the word differentiable on a closed interval, just so you know. But the example we just did was just kind of its own thing. But the one-side derivatives, that's going to be kind of interesting. Here H is positive, here H is negative. But H is a very small number, like H is like roughly like 0.001, you could say here, where H would be like roughly -0.001. Okay. So y equals 2x squared, I know it looks like this. Starting at 1, it should be 2, but it's a hole there, right? Plug in 2, I should get 8, I think. Is that right? Yeah. And then here, 5x minus 3. But plug in 1, I do get and slope is 5. So I plug in oh geez. So they do link up, but we're going to call this a sharp corner. Call this a sharp corner. And you're asked to find one side derivative. So we're going to do the right-hand derivative. Okay, the right-hand derivative is going to be written like this. And we're doing this at what? At a 1. Now, H is positive. H is positive. Which one am I going to plug into? The first or second equation, guys? Because if H is positive, 1 plus H is more than 1, right? Well, the first one's X is less than 1. It's got to be a second. You guys see why it's the second one? Because H is approaching 0 from the right side. So H is slightly positive. And if you're doing 1 plus H, that's 1.00 something. You got to use that second equation. So it'll be 5 times 1 plus H minus 3. And then f of 1, of course, is 2. We know this. So if I find that derivative, you should get, I think, I need a little more space here. You just get 5. So you get 5h over h, and those cancel. So you just get 5. So that's your right-hand derivative. Your right-hand derivative is going to be, oh, did I just mess up this graph? Sorry, guys. Wow. It's Friday afternoon. I apologize. I totally messed up that graph. Okay, I did the algebra correctly. Sorry, 5x minus 3 when x is bigger than 1. Oh, my goodness. Can't believe I did that. My apologies. And then this here, my apologies. Okay, that's still a sharp corner, though. All right, now if I do the left-hand derivative, it's going to get a little dicey here. As soon as h approaches 0 from the left side of f of x equals the limit as h approaches 0 from the left. Now, in this case, you're doing f of 1, well, still doing f of 1 plus h minus f of 1. And I'm out of space here, so I'll have to erase the other stuff. Okay. So f of 1 I know is 2 again. But now 1 plus h is less than 1, right? So I have that. Right, I got to plug into that one. Geez, still not enough room. 2, 1. Those cancel. You factor on h and a 2. And then those cancel. So what do you get for your left-hand derivative? You get 4. So the left-hand derivative is 4. I got lazy. I should have wrote the limit notation. My bad. But for the right-hand derivative, I got 5. What this tells me is that this won't be differentiable at x equals 1 because LHC did not equal RHC. We'll have that discussion more so on Monday. Okay, last one here. Just to close the loop. F is 0, 0. F is continuous. There's no breaks. In the graph of F. This is a slope of 2. Slope of -1. And this happens at 1. So the slope is -1 when you're less than 1. When x is less than 1, the slope is -1. So it's going to look kind of like this. And the slope is 2. You are correct. It's Friday afternoon. You are correct. You are correct. It's -1. Yes, thank you. I need some seam off. There you go. It's like that. And we're not differentiable at 1 because there's a sharp corner there. Because the derivative does not exist at 1. Because we talked about this whole left-right-hand derivative thing. We'll have more of that discussion on Monday about differentiability. When the left-hand derivative doesn't equal the right-hand derivative, that's a problem. So, okay, I feel good. We got the notes done. Homework will be this right here. This handout. You guys already have it. It's just going to be talking about the limit definition of the derivative, working it out. It's actually pretty straightforward. And now you're familiar with the notation. We kind of mix up the notation a little bit so you get comfortable with that. And you should have the answers as well. And I think we're all set. Perfect.